Welcome to Lesson 4.9, Oxidation Reduction Reactions. This is the last type of reaction we're going to talk about in this chapter. Oxidation reduction reactions involve the transfer of one or more electrons. In oxidation reduction reactions, one of the most prevalent type is a combustion reaction. A combustion reaction is anytime you burn a hydrocarbon in the presence of oxygen and get carbon dioxide and water. So if you see a combustion reaction, you can automatically say that's an oxidation reduction, or as we affectionately call it, a redox reaction. Another example of a common oxidation reduction or redox reaction is a metal combining with a nonmetal. In this case, we have sodium, and this is elemental sodium. It is silver. It's a very soft metal. Most times, people look at when they try to picture sodium, they think sodium chloride, but sodium is actually a metal, and it's a very soft silvery metal. When sodium combines with chlorine gas, which is a nonmetal, this reaction is very exothermic, and so we get some flame there and some heat generated. In the end, what we end up with is sodium chloride, and that's what you normally see on your table is that sodium chloride. When we do oxidation reduction reactions, you must know how to assign oxidation states. And so we assign oxidation states with oxidation numbers. It's very easy to confuse oxidation numbers with charges, and those two things kind of mix when we're talking about oxidation reduction reactions, especially if we're dealing with metal, nonmetal compounds. So it's not necessarily a bad thing to get them confused in your head, because it's not going to mess you up in terms of assigning oxidation numbers. But for atoms in a covalent compound, the oxidation state refers to that imaginary charge the atoms would have if the shared electrons were equally divided between identical atoms bonded to each other. So, for example, if we had O2, the electrons should be the same on this oxygen as they are on this oxygen. In different atoms, the shared electrons were all assigned to the atom in each bond that has a greater electron affinity. And so, for example, a metal-nonmetal compound, or even like a hydrogen fluoride, where fluorine's more electronegative, then the extra electrons would go towards that fluoride ion instead of the hydrogen ion. For ionic compounds that contain monatomic ions, the oxidation states of the ions are equal to the ion charges. So oxidation states equals ion charges here. So for example, sodium ion, that's a monatomic ion, so the oxidation state is +1. For electrically neutral compounds, the sum of the oxidation states must be 0. So for example, if I have sodium chloride, I know that a sodium ion is a +1, a chloride ion is a -1, and that equals 0. So that's the same thing we talked about when we were naming compounds and writing formulas for compounds. For an ion, the sum of the oxidation states must equal the charge of the ion. So for example, if I have nitrate ion, that means whatever charge is on my nitrogen plus whatever charge is on my oxygen, well, my 3 oxygens, must equal -1 instead of 0 like it was up here. And oxidation states are simply just written as plus or minus. This is another tool for assigning oxidation states. An atom in an element is 0. So anytime something is in its elemental state, then the oxidation state is 0. A monatomic ion is the same as its charge, so it gives examples here of sodium and chloride. Sodium is a +1, chloride's a -1. Fluorine is -1 in its compound, so that's just kind of a general rule. Fluorine is always a -1, so anytime you see it in a compound, -1, that's its oxidation state. Oxygen, most of the time, is -2. The only exception that you'll run across is in a peroxide, where in a peroxide polyatomic ion, it is -1. Hydrogen is +1 in its covalent compounds. And so anytime it's a covalent compound, which is a nonmetal, then it is a +1. Just a critical thinking question they threw in here. What if the oxidation state for oxygen was defined as -1 instead of -2? What effect, if any, would it have on the oxidation state of hydrogen? I my guess here is, and you might have some other thoughts on this, is that it would just, it would change incrementally. So, for example, water would probably just be HO instead of H2O, and you could probably come up with other examples if you want to stop and think about that. So we're going to go through this example. The next few slides go through each assigning of the oxidation states in very detailed, but we're going to go ahead and I'm going to, since I have plenty of room on this slide, I'm going to run through this, and we're going to assign oxidation states just on this slide, and then you can go through the following slides. I'll scroll through them quickly, but you can go through them on your own at a slower pace if you'd like to. So according to that last slide, if we're going to look at A here, we're going to look at carbon dioxide. According to that last slide, oxygen should always be assigned a -2. So in this particular example, my oxidation state, so we're going to do this one first, oxygen is going to be -2. Now, how many oxygens do we have? We have 2 oxygens, so the total oxidation state of my oxygen is -4. And since this compound has to equal 0 because it's a neutral compound, that means the oxidation state assigned to the carbon or carbons would be +4, and since there's only one carbon, then carbon's oxidation state is going to be +4. Okay, does that make sense? Let's go ahead and erase that and kind of get that out of the way, and then we'll do this next one. Again, we have oxygen in this compound, and so we're going to assign it a -2. So oxygen is -2. Its total is going to be -6. So oxygen itself is -2. Its total is -6. Now, this has that minus indicates that the charge on the total ion is -1. So X plus -6 equals -1. So that means the total charge on the nitrogen must be +5, and since there's only one of them, that whole nitrogen carries that whole +5 charge. Okay, so as I said before, I'm going to scroll quickly through the next few slides because these are the same thing we just did, but you can scroll through them slower if you'd like. Now, this is where it gets a little bit more complicated, and this is where I recommended that you perhaps look at these and stop and process. So we're going to go through each of these, and I'm going to erase when we're done, and the answers will show up on the slide as soon as I hit the enter. But let's go through these. So let's do potassium permanganate first. In this particular example, oxygen is always a -2. So oxygen is -2. Now we have 4 of those, so we're going to have a total of -8 on the oxygen. We're going to skip manganese for just a little bit because manganese is a transition metal and it's in the middle of the periodic table. So we don't automatically know what its charge is, but we do know what the charge of potassium is because potassium is in that first column. So the oxidation state we're going to assign potassium is +1, just like we would if it was an ion. So there's one of those. So now we have a +1. If we look at this, what we have currently over here, that's going to total, if we add those up, that's going to total -7. We need this compound to be neutral. So in order for it to be neutral, we need to assign the manganese a charge of +7. Sorry, I can't read that very well. +7. Okay, so stop and process that for a little bit if you need to. And then I'm going to go ahead and erase, and we're going to go on to the next example. And sometimes it's easier to go, when you go through these, to do them in small chunks. And so that's what we're going to do on this next one. We're going to look at that hydroxide first. Hydroxide we know is a -1. So oxygen, we're going to assign it a -2. Hydrogen, according to our rules, will always be a +1. Okay, so the total of this is -1. But I mean, this is what we need to know. But we need this -1 out here. But we have 6 of those. So the total on this chunk right here is -6. Okay. We know that a sodium is +1 because it's in that first column, and its oxidation state is going to be the same as its charge. There are 4 of those, so that means that's a +4. Now, if we total that, that gives us a -2. We still have one element that we can assign an oxidation state to make that compound be 0. So that is that iron, and we're going to give it a +2 charge. So I chunked that a little bit because I knew the polyatomic ions charge. So again, stop if you need to, process that, and you can even try that on your own if you want again. The next one, we're going to do the same thing here. We're going to go ahead and chunk that ammonium compound, and we're going to hydrogen in a compound like that is always a +1, and so that's going to make our nitrogen, because there's 4 of those, so this is going to be +4. And this is an ammonium, and so an ammonium ion needs to be a total of +1. So if our hydrogen is a +4, that means our nitrogen has to be a -3. So we're going to, so I used just simply the fact that I knew ammonium ion was a +1, and I worked backwards from there. This is going to be, the total is going to be a +1 on this. We're going to take that times 2 because there's 2 of them, so that's a +2. Oxygen is going to be a -2. And again, in this case, there's going to be another +1 over there. So just bear with me just a second. Okay, so oxygen is going to have a -8. Now, we've dealt with this atom, we've dealt with this hydrogen, we've dealt with this. This hydrogen itself is also going to be a +1. So we've got another hydrogen in there that's a +1. Okay, so now if we total that up, that makes our total -5 on this neutral compound. So that means we need to assign a +5 to that phosphorus. Again, I encourage you, strongly encourage you to stop and process that for a while. Work backwards on your own. See if you can do that one yourself, because that one was a tough one. Now we're going to look at glucose, which is this last one down here. You've probably seen this in your biology course. And we are going to start with the rules. Oxygen, -2. Hydrogen, a +1. So if we take that times 6, we end up with -12. And we take that times 12, we end up with +12, which is 0, which indicates to us that carbon's oxidation state is going to be 0 in this compound, because we don't need any additional numbers to balance that out. So let me go ahead and erase that, and we will see what the slide tells us about what the answers are. And there you go. Like I said, you can work through those on your own if you'd like, or you can just kind of go on through the slide. Okay, so in an oxidation reduction reaction, so what we just did was we assigned oxidation states, and the reason you assign oxidation states is because in an oxidation reduction reaction, you need to figure out the transfer of electrons and which atom is oxidized, which one is reduced, which one's the oxidizing agent, which one's the reducing agent. So we simply transfer electrons, and the reason that compounds transfer electrons, or atoms transfer electrons, is because they want to become more stable. So oxidation reduction, an oxidation is an increase in the oxidation state, a reduction is a decrease in the oxidation state. And to be honest with you, the way I remember it is reduction, the charge goes down because it's reduced, and then I work backwards from there to remember what oxidation is. So an oxidation is the loss of electrons, and the reduction is the gain of electrons. The oxidizing agent is the electron acceptor. So the oxidizing agent is actually the one that's reduced. And then the reducing agent is the electron donor. That's the one that's actually oxidized, because electron acceptor goes with gain, electron donor goes with loss. Okay. Just this little particular diagram summarizes what's happening in an oxidation reduction reaction. So this next example talks us through basically a real life process. When we produce a metal from its ore, it's called metallurgy. It always involves an oxidation reduction reaction. So what you have is you have a metal that's in a compound, and we want the metal all by itself. So in this particular process, we have galena, and we're going to convert it first to lead sulfide. Sorry, we're going to convert it first to lead oxide. We're going to roast it. And so if you look at this particular process, any element by itself has an oxidation state of 0. And a lot of times I'll write oxidation states if I'm trying to figure them out up above the atoms themselves. Anytime oxygen's in a compound, it's -2. And so we're going to work backwards from here and figure out what the charges are on the others. Lead sulfide, when sulfur's in a compound, it's a -2 because it's in the same row as oxygen. Can't write that very well there. And so that means, to balance this out, that lead has to be a +2. So we've got +2, -2, and 0 on the reactant side. Over here, this lead is also going to be a +2 because it's a 1-to-1. This sulfur, though, has changed charge, and it's going to be a changed oxidation state. And so it's going to be a +4 because we need to balance out that compound. And so that's how you look at a reaction and go through and assign oxidation states. The second step of this process, we take that lead oxide and we treat it with carbon monoxide to produce lead metal and carbon dioxide. And so again, we're going to go through and we're going to identify the atoms that are oxidized and reduced and specify the oxidizing and reducing agents. And we're going to go back and do that on the slide prior as well. Remember, if it's in its elemental state, it's 0. Oxygen's -2. When it's in a compound. So that means that lead's a +2, that carbon has to be a +2, and this carbon has to be a +4. So if something is oxidized, that means its charge goes up because it lost electrons. And so in this particular case, oxygen stayed the same every time. So we're not even looking at oxygen. So we're looking at what happened to carbon and what happened to lead. So whose charge went up? Okay, carbon's charge went up, so carbon is oxidized. So therefore it's the reducing agent. And lead was reduced, therefore it's the oxidizing agent. Okay, again, process that. I'm going to slip back to the last slide and we're going to look here. On this one, oxygen did not stay the same on both sides. Oxygen went down in charge, so oxygen is reduced in this particular instance. And so it's the oxidizing agent. And then in this case, lead stayed the same. So we're not looking at lead, but sulfur, its charge went up, and so it lost electrons, so it was oxidized, and because it donated those electrons, it was called the reducing agent. This does take a while because you do have to assign oxidation states, and then you have to process what's going on. Again, these slides are taking you through the process of what we just did. I thought this critical thinking question was rather interesting. Dalton believed that atoms were indivisible. Thomson and Rutherford showed him this was not true. What if atoms were indivisible? How would this affect the type of reactions you've learned about in this chapter? So, for instance, what we just talked about, if something loses or gains electrons, that's part of an atom. And if it were indivisible, we would not have oxidation reduction reactions. So that's an interesting thought. For the reaction of sodium bromide with chlorine gas to form sodium chloride and bromine, what are the appropriate half reactions? And this is just kind of leading us into the next lesson, which is going to be 410. It's going to be balancing oxidation reduction reactions. What we do need to do is we do need to draw this reaction. So the reaction of sodium bromide with chlorine gas forms sodium chloride and bromine gas, and these need a 2 because they're diatomic. And so what that causes us to do is it causes us to have to put a 2 there. Now, in this particular reaction, sodium is going to be a +1 on both sides. So it's kind of like our spectator ion. And so what we're going to have is we're going to have 2 bromines over here, and they're going to go to bromine gas and 2 electrons because we want the charges to equal on each side of the arrow, and we can only add electrons. So since we had a -2 over here, we're going to add 2 electrons on this side. Now chlorine gas, Cl2, is going to 2 Cl minuses because that's what happens when it's in this compound. Again, I have a -2 over here, so I need to add 2 electrons on this side. And so what we have is we have these are our 2 half reactions. And that the only ones showing that is answer choice B. Again, you'll see this in the next lesson, so don't panic if you don't understand it now. Oxidation, so how many of the following are oxidation reduction reactions? And what you're doing is on this one, you're just simply looking for if something changes charge. So in this particular case, that's a 0. Chlorine's a -1, making that a +3, -1, +5, so that one is. In this one, copper is a 0 going to because nitrate's a 2, or there's nitrate's a -1 times 2 makes that +2, so that's an oxidation reduction reaction. In this one, oxygen's always a -2, hydrogen's always a +1, lithium's always a +1. So what we need to do is we need to look on that carbon and see if anything happened to the charge on it. So -6 +1 or +2 makes this a +4, and that one's a +4. So this one is not an oxidation reduction reaction. This iron's a +2 on this side because the chlorine's a -1. It's also a +2 on that side, and so that one is not. So the correct choice is, answer is C, because 2 of those are oxidation reduction reactions. Which of the following is not an oxidation reduction reaction? So we've went through and we've talked about this one in this presentation. We've also talked about this one. This one is a metal with an acid. So this would be like taking magnesium and combining it with hydrochloric acid. Anytime that happens, you get hydrogen gas and then the metal salt. So that means this is also an oxidation reduction reaction. And so the only choice is precipitation reactions because things don't change charge on that one. Real simple problem here. So oxygen's a -2. So it's a total of -4. That means this carbon has to be a +4 to get that to balance out. So answer choice, answer choice, answer choice. And now let's look at this one. The second one, oxygen is a -2, but I have 3 of them, so that's a total of -6. My total compound charge must be -2, so that means my carbon has to be +4. So my answer choice on that one is E. This unbalanced reaction, this is just what actually the exact same reaction, only not balanced, that I showed you before. This is an oxidation reduction reaction because magnesium's going from a 0 to a +2, and hydrogen is going from a +1 to a 0. Each of the following results in chemical reaction, which is not an oxidation reduction reaction. Methane gas is burned in air. That one is an oxidation reduction reaction because remember, any hydrocarbon combustion process is oxidation reduction. Iodine crystals are added to an aqueous solution of silver nitrate. A piece of silver metal is placed in an aqueous solution of copper 2 nitrate. So anytime you have an element and it says it results in a chemical reaction, so a reaction occurred, that means that element's being combined with something, and so those have to change charge because they go from 0 to something else. Chlorine gas is bubbled through a solution of aqueous sodium bromide, so again you have an element going through a process, and so that kind of leaves us with this. Aqueous solutions of lead 2 nitrate and sodium iodide are mixed together. That's a precipitation reaction, and so that's going to be your correct choice. That one is not an oxidation reduction reaction. And I'm pretty sure this is the last slide. Finally, yay. So what we're doing is we're trying to figure out which nitrogen has the highest oxidation number. And remember, we're going to, so let's start here at the bottom. This oxygen's -2, so that nitrogen has to be +2. This one is in its elemental state, so that one's 0. Chlorine's a -1, so that nitrogen has to be a +3. Oxygen's a -2, so that one nitrogen needs to be a +4 to balance that out. And in this particular case, since that nitrogen's a, or sorry, the hydrogen's a +1, then that nitrogen has to be a -3. And so our answer choice on this one is question B. And I encourage you to strongly go through this particular example on your own, because I do see this a lot in the question bank. All right, that ends lesson 4.9. Next lesson will be about balancing redox reactions.